This lab is for exploring the hydraulic jump phenomena. The objective of this lab is to calculate the flow rate, energy loss through the hydraulic jump, and to verify the specific energy. Before getting started with the lab, let's see some of the important terms that we are going to encounter. The first important term is the critical depth. The critical depth of the flow only depends on the flow rate and the channel geometry. Water flowing at a critical depth also has the minimum specific energy and a Froude number equal to 1. Using critical depth, we can classify if the flow regime is supercritical or subcritical. Which brings us to supercritical flow. The supercritical flow has a flow depth shallower than the critical depth. They also have a Froude number greater than 1. The subcritical flow, on the other hand, has a flow depth greater than the critical depth and a Froude number less than 1. Subcritical flow are the most common type of flow in nature. With the two types of flow regimes defined, we can now define the hydraulic jump, which occurs when a zone of supercritical flow discharges into a zone of subcritical flow, causing the depth of water to cross the critical depth. The transition between the two regimes is associated with a large amount of energy being dissipated. This is primarily why hydraulic jumps are designed as energy dissipation systems in the spillways and the outlets. A momentum conservation equation is used to derive the change in specific energy and the ratio of depths across the jump. Now that we have revisited some of the key terms, we are now ready to head into the lab and create some hydraulic jumps. But before turning on the pumps, let's get a general overview of the lab setup. When we start the pump, the water flows into the head tank and comes out as supercritical flow from the head gate orifice to the rectangular fume. The angle of the tailgate at the end of the fume is then adjusted by a lever to create a subcritical flow and form a hydraulic jump. We take the measurements across the jump and also note down the distances from the tailgate. We also note down the distance to where the hydraulic jump is formed. Now to the lab. As we turn on the pump, the water fills up in the head tank and rushes out from the head gate into the rectangular fume. The water comes out of the head gate at a very fast velocity and makes its way to the tailgate. We gradually increase the angle of the tailgate with the control lever to form a subcritical depth at the downstream and create a hydraulic jump. The next step is to measure the flow rate. The water from the outlet makes its way into the weighing tank. We record the time taken for the weighing tank to reach from the initial to final weight to calculate the flow discharge. We repeat this procedure 3 times and note the weight and time for each iteration. After we have the required measurements to calculate the discharge, we measure the width of the rectangular fume and draw the profile of the water in the fume. The 3 depths Y1, Y2, and Y3 are then marked, and their depths are measured. We also measure their distance from the tailgate. We then take the measurement of depth of water in the flow tank Y0 using the water level. We can use this value to get the velocity P1 at the supercritical flow to compare the results to what we obtained from the direct discharge measurements. It should be noted that we have not considered the head loss through the orifice, and the result of the two velocities can be very different. Be sure to include that in the discussion section of your report. We repeat the entire process with a smaller discharge. We can see the hydraulic jump move upstream with the lower discharge. The final recordings of the two experiments for calculating the discharge is shown in the table. Please pause this video to note down the values. Similarly, here are the readings of the flow depths and their distance from the tailgate for the two experiments. Use these values to work out the requirements in the results section of the lab sheet.